What's kind of weird about this is we have an entire unit in AP Chemistry dealing with acids and bases, where we have to get really in depth into a lot of things. However, since an acid and a base can come together and react, that is part of our reaction unit. So we do have to kind of gloss over some material right now dealing with this. And primarily, I looked at what were their goals when they set up this topic on the sheets that you pick up on the way in. And I tried to give you that information here. Again, my focus is more on the reactions and the math behind it instead of what makes this an acid, because we are more than enough going to cover that second semester. However, basically what we're doing is reviewing Chem 1 with today's notes. So, in Chem 1, we spoke of two different ways of defining something as an acid. You're not going to have to notice the difference between the two, but if this is meant to be giving you a little bit of a reminder of what makes something an acid, it is worthwhile to go over. The Arrhenius definition is anything that creates hydronium ion in solution. Now I give you that balanced equation, and on the product side, the H3O plus is the hydronium ion. The presence of that in solution is what makes it an acid for the HCl's case. Acids are good at conducting electricity. If you've ever heard of battery acid before, well, it has ions in solution at the final product. So it must be good at conducting electricity because you need charged particles in order to conduct electricity. So again, that's our original definition of an acid. Our original definition of a base is anything that creates hydroxide in solution. Now the equation I give you on the bottom is a covalent base. Ammonia, which is NH3, plus H2O, making ammonium polyatomic ion and hydroxide. The most common bases are actually ionic things that end in OH, like NaOH. Sodium hydroxide is far and away the most common base used in laboratories for acid-base chemistry. So I wanted to give you one that was a little more indirect to show that it's a base. Technically, what you'll learn second semester is my arrow going from reactant to product should be a double equilibrium type arrow, but we'll get into strengths of acids and bases second semester. That's when things get good though. So. Oh, I'll even briefly mention where you even kick it up a notch beyond that. So in Chem 1, this is the first thing we told you about acids and bases. What makes an acid, what makes it a base? Well, you put it in water, what does it make? Does it make the hydronium? It's an acid. Does it make the hydroxide? It's a base. If it makes neither, it's not an acid or it's a base. It's just a neutral thing. And there's plenty of neutral things out there. Now the second definition of what makes it an acid or base, you don't need the water component. And that's the more common definition. There's actually a third definition that we no longer really have to cover. And actually your goal sheet even mentions that Lewis acids are excluded from this. A Bronsted-Lowry, which were two separate scientists around the same time. A Bronsted-Lowry acid is anything that can give away an H+. H+ is the shorthand notation for a proton. Because if you think of a hydrogen atom has one proton in its nucleus and an electron orbiting around. If you lose that one electron, all you have left is a proton. And that hydrogen would have a +1 charge because it lost an electron. So that's why H+ is often used as shorthand notation for that. Quite frankly, why do we write the formulas the way that we do at times? We put hydrogens in the front of things to show that it will donate that hydrogen. Because if you recall, when I showed you a base before of NH3, the hydrogens are put on the back end. Because if we called it H3N, you might think that it's an acid. So if it starts with that H, it could probably donate that H. Bases are the things that accept protons. Once you're done writing that down, I'm going to switch over to the Smart Notebook, and I'm going to kind of draw this out in a Lewis dot style to show you that these two definitions work hand in hand, especially when it's dealt with in water. Here's HCl. There's H2O. Both of these are polar covalent molecules, where the hydrogen on both ends is the partial positive, then either the oxygen or the chlorine is the partial negative. When you add HCl to water, they're all mixing together, they're all bumping into each other. And what can happen is the partial negative end of water, with its two lone electrons, can bump into the partial positive end of the HCl. It can create an attraction. After all, this end is partial negative and this end is partial positive. That attraction, along with the fact that there are lone unbonded electrons here, can create a bond. It can take that H away from this. Now, hydrogen can't be bonded to two things at once, so what happens is those electrons in that bond, they get broken and they're around the chlorine, which is why your final products here is chlorine, now with 8 electrons around it. That's why it has a -1 charge, because its formal charge is now a -1. And the water has one more H bond than normal. Again, hydronium is a +1 charge because remember, oxygen should have 6 electrons around it. Currently, oxygen has 5 directly around it as a formal charge of +1. I'm trying to remind you of vocabulary we did in the last unit because it all ties together. Now, the base example I gave you was ammonia. Ammonia is also a polar covalent molecule. However, in this one, those electrons on the nitrogen attract the hydrogen to create a bond, which means this HO bond gets broken. Leading us to our products of the ammonium polyatomic ion and the hydroxide, which is actually also a polyatomic ion. Something that we will definitely get into more in the second semester is water in the first one accepts an H+. That means water is acting as a base, according to the Bronsted-Lowry definition. In the second problem, water is donating the H+. It's acting like an acid, according to Bronsted-Lowry. That being able to act as either an acid or a base, depending upon what you are around, is referred to as an amphoteric property. Again, we have to go much more in depth second semester in acids and bases. What I want you to get out of this is recognition of the hydronium ion for an acid, hydroxide ion for a base, and then just look at the formula. If it leads with a hydrogen, that's a good indicator that's an acid, unlike that NH3, which we write it as NH3 for a reason, to show that it is not an acid. Okay, the reason why we have to go over that intro is to remind you of we are in a reaction unit, and a very common reaction is a neutralization reaction. That's where you take an acid and a base and you put them together. It works kind of in the same mechanism of double displacement, where water and then some sort of ionic compound are created. So up on the board I have for a second bullet point, the simplest, most common neutralization reaction done in chemistry laboratories. Hydrochloric acid with sodium hydroxide. My third bullet point is the net ionic equation. Net ionic equations don't have to only be done for things that create solid precipitates. It can be done for something that creates a pure liquid, like water, or something that creates a pure gas. Typically, these are written for either single or double displacement reactions. And for the most part, when this occurs, if they are combined in the correct stoichiometric ratio, which is why we have to do a little math with this in a little bit, it should make a neutral solution, hence a neutralization reaction. Sometimes that ionic salt can actually react with water in something called hydrolysis and can make it actually slightly acidic or slightly basic. That's when things get really weird. You've got probably until either late March or early April before we get to that spot. By the way, the last bullet point on here, in Chem 1, because again, I'm trying to review Chem 1, we talked about a second type of acid-base reaction, where the base is something that contains the carbonate polyatomic ion. In that one, not only is water and an ionic compound produced, but so is carbon dioxide. This particular reaction up on the board is hydrochloric acid plus sodium bicarbonate. This is what we would do if we spilled hydrochloric acid on the lab bench. Baking soda, next to the fume hood, we pour on top of it. Baking soda is sodium bicarbonate. And what it would do is it would neutralize. How do you know it's done neutralizing? It would stop creating carbon dioxide bubbles. Okay? 2 more slides to go. One is to remind you of the pH scale. There's 2 ways that we can measure how acidic or how basic something is. One is by molarity. If you see an acid with a high molarity, it's really acidic. You see a base with a high molarity, it's really basic. Now again, second semester, I have to undo that simplification to a certain extent. However, for right now, that should hold true. The pH scale, I say, typically runs from 0 to 14 because you can actually exceed 0. You can get to the negatives. You can exceed 14. Just high enough concentration, strong enough acid or base. However, at room temperature, that's another weird thing that we have to go over next semester. At room temperature, neutral is a pH of 7. The vast majority of solutions that we work with are a pH of 7. You dissolve sodium chloride in water, it's a pH of 7. A lot of those double displacement reactions that we do where you have an aqueous at the end, it's going to be a pH of 7. However, some things will have a pH below 7 because they are more acidic. Some things will be above 7 because they're more basic. The further away you get from 7, the more acidic or the more basic you are. The last thing I note is to remind you that when we talked about this in Chem 1, the pH scale is a power of 10 scale. For example, if you had 1 molar HCl, that would be a pH of 0. If it was 0.1 molar, so 10 times less concentrated, that'd be a pH of 1. If it was 10 molar HCl, it'd be a pH of -1. So the power of 10 scale, used in earthquakes, the logarithm thing that perhaps math classes have talked about, is something that we talked about as well. Last thing, I want to remind you about titration and then the math behind titration. Again, on the goal sheet you picked up on the way in, one side talked about acid-base reactions, the other one talked about titration. Remember, titration, we use a burette, a long glass tube. We'll be doing titrations in a little over a week. However, we're going to combine titrations with oxidation and reduction. So it doesn't have to just be done for acid-base chemistry. In Chem 1, we did it for acid-base chemistry. Typically, the point of titration is to find the concentration of something that you don't know. And I give you an example problem up on the bottom there that I'm going to show you here in a little bit. What you would do is put in the burette what you do know the concentration of. And then you can add that to what you don't know the concentration of. Because the burette will give you a volume of a known thing. Notice this problem here, 32.7 milliliters of 0.0250 molar HCl. So it give you that concentration. If you know the volume of your flask underneath, 20 mils of NaOH, then when you reach that equivalence point, when the acid and the base have balanced each other out, you can do a little math to figure out what the concentration is. Again, that's typically what we'll do with titration. You need an indicator like phenolphthalein, if you remember going from clear to pink when we did that in Chem 1. But what I want to do to wrap up notes here is I want to go over how to solve this particular problem, which is solution stoichiometry. So it's nothing new necessarily, because we actually covered this in Chem 1 as well. However, we've been just going over different ways of showing stoichiometry for the past over 2 weeks. So this is kind of wrapping that up. Now, there's two ways you can go about solving this. You can do kind of the stoichiometry conversion method, which is what I'm going to show you. Or you can remember, if it's solutions, we can use that molarity equation. Molarity equals moles divided by liters to solve for there. But in this question, we were given 0.0327 liters of HCl. And I was given the molarity as well, 0.0250. That's how many moles are in 1 liter if it's molarity. So if I was doing this problem, I'd first figure out how many moles of acid do I have. Recall that liters on the top, liters on the bottom cancels out. I'd be left with moles of HCl. And if you don't like this method, you can just solve molarity times liters equals moles. I have no problem with that. Step 2 is I need to convert to NaOH from HCl. In this particular equation, it's a 1-to-1 ratio. I actually had the equation earlier in the notes, that's why I didn't rewrite it. But this is your stoich step, and why you should have a balanced equation. And if you're someone who wants to do molarity times liters equals moles as your step number 1, so again, here's my step number 1, here's my step number 1. Everyone has to do the same step number 2 of use the balanced equation coefficients. By doing that, HCl cancels out top and bottom. Now I'm in moles of NaOH. I want to solve for the molarity. And it gave me 20 milliliters. I'm taking moles divided by liters. And again, if you don't like that method, this is all I'm doing for step number 3. Either method should hopefully give you the same answer, 0.0409 molar NaOH. I mean, I could have you solve for the volume as well. How much is required to neutralize this? But my goal for the rest of class today is to practice this solution stoichiometry.